All right, today we are diving deep into the microscopic world of silicon chip design. It's a world so complex, it's honestly less like engineering and more like, well, like building an entire civilization from the ground up. Let's get into it. And that's not just some philosophical question, right? It's the real, fundamental problem every single chip designer has to solve. You gotta understand, a modern chip isn't just a circuit. It's a microscopic metropolis. We're talking billions of transistors acting as its buildings, all connected by this insane labyrinth of wires. And today, yeah, we're gonna build one. So, here's the game plan. We'll start with the architect's vision, lay out the city zones, place every single building, build all the roads, run a full citywide inspection, and then finally, hand over the master plan to the builders. Okay, so first things first. Just like any great city, it all starts with a plan. And for our chip, that means before a single wire or transistor is even thought about, engineers have to create the master blueprint that defines what this thing is even supposed to do. So this is the big picture stage, you know? What is this chip going to be? Is it a GPU for a gaming rig? The brains of a new smartphone? Engineers spec out everything, what it needs to accomplish, how fast it has to be, and exactly how much power it's allowed to drink. These specs, they're basically the laws of our new city. Non-negotiable. Okay, so how do you get from these high-level ideas to an actual functional blueprint? Well, you write code. Using special languages like Verilog, engineers describe the flow of data and all the logic operations. This is called register transfer level, or RTL. And what's absolutely crucial to get here is that this code, it isn't describing physical transistors just yet. No. It's describing behavior. This is the constitution for our entire city, the set of rules everything will follow. All right, the blueprint is written, but now we hit our first huge wall. The sheer, insane scale of this thing. A design with billions of parts is just way too complicated to handle all at once. You have to break it down into manageable chunks. The very first step in the physical design is something called partitioning. Think of it like a city planner literally taking a giant map and drawing lines to create different districts. Here's the financial district. Over here are the residential areas, and that's the industrial zone. By grouping related functions together, you make the whole problem manageable, and, this is key, you cut down on the traffic, or the number of connections needed between all those districts. So you've got your districts, right? Now you got to figure out where they all go. And that is floor planning. Where's the main CPU core going to live? Where are we putting the big memory blocks? And how are we going to position the I/O pads that connect our tiny city to the outside world? This whole stage basically defines the chip's overall geography. And this image here, it shows you exactly what I'm talking about. You can actually see these separate blocks. And look, they each have their own infrastructure, like these local power rings. Eventually, they'll all get hooked up to the main power grid that runs the whole chip. It's all about getting that high-level, organized layout down before we get lost in the weeds. Okay, so our city is zoned out. We've got our districts. Now comes the part that is, honestly, just mind-boggling. We have to decide the exact location for every single one of its billions of buildings. You see, each of these standard cells is like a basic building block, a simple logic gate. Placement is the process of giving every single one a specific coordinate on the silicon. It's like assigning a unique street address to every single house, every office, and every factory in our entire city. I mean, it sounds simple enough, right? It's just a puzzle. You just try out every combination until you find the one with the shortest wires and the best performance. But the scale we're talking about, it makes that completely, utterly impossible. Get this. To find the absolute, mathematically perfect placement for just 20 little components by brute forcing every single possibility, it would take a modern computer over 77,000 years. Yeah, now try to imagine that for billions of them. It's just no way. So, since finding that perfect solution is literally impossible, designers have to rely on these really clever shortcuts. They're called heuristic algorithms. These are incredibly sophisticated methods that don't just check every option. Instead, they use smart strategies to find a solution that's, good enough in a reasonable amount of time. And these ridiculously complex algorithms, they aren't written by the chip designers. No way. There's a whole specialized industry for this called electronic design automation, or EDA. Companies like Cadence, Synopsys, and Siemens EDA are the ones developing the multi-million-dollar software tools that make this whole impossible process possible. All right, so all our billions of buildings have an address. They're all placed. But now we got to build the roads, the power lines, the data cables, all the wiring that connects everything together and turns a collection of buildings into a city that actually functions. And just like placement, routing is way too complex to tackle all at once. So they break it into two stages. First, there's global routing. Think of this as planning the major highway system between our different districts, trying to avoid any huge traffic jams. Then there's detailed routing. Now we're down to the street level, assigning each individual wire to a specific metal track on a specific layer, making sure no wires touch and every single design rule is followed to the letter. Okay, our city is planned, it's built, it's all connected. But how in the world do we know if it actually works? I mean, a single bad connection out of billions could break the whole thing. And you can't exactly crack it open and poke around with a multimeter, right? The solution is just brilliant. The idea is, since you can't test it from the outside, you build the testing equipment into the design itself. It's a whole philosophy called Design for Testability, or DFT. It's like building secret inspection tunnels and sensors into every single building while you're constructing the city. And one of the coolest, most powerful DFT techniques is called the scan test. Basically, certain memory components in the design get replaced with these special scan cells. In normal mode, they work just like they're supposed to, but in test mode, this is the cool part, they link up together to form this super long chain, a scan chain, that literally snakes its way through the entire chip. It's our secret inspection tunnel. So here's how this secret tunnel works. First, you shift in a specific pattern of ones and zeros, loading up that chain and setting the chip's internal state to exactly what you want. Then you let the chip run for just one single clock cycle. Just one. Finally, you shift out the result from the chain and compare it to what you expected to see. Any difference? Boom, you found a fault deep inside our microscopic city. So let's recap. We've designed it, we've placed it, we've routed it, and we've even built in a way to test it. Our journey's almost over. There's just one last thing to do. Create the final official blueprint for the manufacturing plant. And that final output, that master plan, is called a GDSI file. This isn't abstract RTL code anymore. Oh no, this is a massive, incredibly detailed data file that describes the precise geometric shapes on every single layer of the chip. This is the master plan that gets sent to the manufacturing plant, or fab. It's the complete journey, from an idea written in RTL all the way down to a concrete set of instructions in a GDSI file. And that, right there, is the incredible journey of silicon design. It's this amazing process that turns pure logic into a physical reality that's almost too complex to imagine. So really, the next time you pick up your phone, take a second. Will you just see a device, or will you see that impossible, microscopic city that you're holding right there in your hand?